Okay, so this is the circuit that we discussed last time. We said that this is a simple CMOS operational amplifier. We talked about the various sub-circuits. We said that the blue part here is the current reference and the current mirror MOSFET. And this part here is a common source amplifier. And this part here implements a differential amplifier using MOSFETs. And this is what we will focus on today. How can we build out of transistors an amplifier that amplifies just the difference between two signals? So how can we build something like this? And what are the characteristics? How can we analyze it, design it, and so on and so forth? So this is the MOSFET differential amplifier, the original or the simplest, I would say, structure for a differential amplifier. Remember that I have two inputs and I want to amplify the difference between them. Okay, Shafi is telling me that my screen is not shared. Okay, well, you did not miss much, so let me resume sharing. Thank you for letting me know. Let's see, resume share. Can you see the PowerPoint moving now? No? Yes? Okay. One second, let me try to share again my screen. PowerPoint share. Okay. Now, can you see the screen now, the PowerPoint updating? All right, okay. All right, so technology works most of the time, and sometimes it doesn't, but that's okay. Again, this is the differential amplifier circuit that we will start with. It's a very simple differential amplifier that's built out of a couple of MOSFETs, and the gate of the first MOSFET is connected to the first input. The gate of the second MOSFET is connected to the second input. And what this amplifier will do, we will show that what it does is amplify the difference between the first input or the signal here and the second input, which is the signal here. And to make this work, I have two resistors, RD and RD, exactly equal, and they're connected to the supply VDD. And the two sources of the MOSFETs are shorted, connected together to a current source that is used to bias these two MOSFETs, and it's connected to the negative supply. So the drains are connected to the resistors, and I take the output, or actually two outputs from them. So I have one output here, VO1, and another output here, VO2. And the gates are connected to the inputs, and the sources are connected together to the DC current source used to bias this amplifier. We have two inputs, VI1, VI2. We want to amplify their difference. And we have two outputs. We have the option of considering this as our output, or considering this as our output, or as we will come and show later, to consider the difference of these two, VO1 minus VO2 or VO2 minus VO1, as the output signal. Right, so let's see how does this work. Let's start by assuming that there is nothing here. There is no signals, or even this is connected, grounded. connected using a wire to ground, and this is connected using a wire to ground. So 0 volt here, 0 volt here. And another assumption that we will make in these circuits is that not just these two resistors are equal, but these two MOSFETs have to be perfectly matched. So this Q1 has the exact same characteristics and parameters and configuration or whatever as Q2. So these Q1 is exactly the same as Q2. So let's say VI1 is 0, VI2 is 0, Q1 and Q2 are perfectly matched, RD is exactly equal to RD, these are connected to the supply, these are connected to the current source here. What would be the current in each MOSFET? Well, again, this is 0 and this is 0. So the two gate voltages are equal. These are connected together. These are equal. These are perfectly matched. And I have a current flowing here, which is the sum of this current plus this current. That's KCL. This current, ID1 plus ID2, should be equal to I. But because of the perfect symmetry in the circuit, it's perfectly symmetrical. There is nothing that says that this side is different from this side. When this is 0, and everything else is exactly the same. This current, therefore, must be equal to this current due to the perfect symmetry. And if their sum is I, then ID1 plus ID2 is equal to I, and ID1 is equal to ID2, which means that ID1 and ID2 are I over 2. So I'll have a current here, I over 2 flowing, and a current here, I over 2 flowing. And that's it. A question by Jason, why do we have a minus VSS? We have a minus VSS and a plus VDD to allow a swing in the signal around ground. As you can see here, if there's no DC component in VI1, the signal will swing around ground, around 0. Same here. To allow that without turning off the MOSFETs, without causing the MOSFET to go to cutoff, I need a negative supply here so that when this drops below 0, VGS of this will continue to be positive and this will continue to conduct. To be able to do that, to be able to have a signal that swings around ground, around 0 volt, I have to make this into a negative voltage, and that's why we use a negative supply. If we don't use a negative supply, if we have a ground here, then VI1 and VI2 cannot swing around the ground. They will have to vary around some DC level. And that's possible. Some op-amps operate like that. They operate between a positive supply and ground. But then you cannot apply your signals without any DC bias and a DC offset. You need to apply your signal around some DC level. To be able to just apply the signal as is around 0, we use a negative supply. Okay, so again, when these two are 0, 0, the two currents are equal, what would be the output? The output would be the voltage here is the supply minus the drop in RD. So VDD minus RD times the current here. The current here is I over 2. So VDD minus RD times I over 2. That's VO1. And what's the voltage here? VDD minus RD times I over 2. I is a DC current. So I over 2 is a DC current, is a fixed value. RD is constant, VDD is constant. So VDD minus RD times I over 2 is a constant level, the DC level here. Let me write it. Let's see. Write it right here that this is when VI1 is equal to VI2 equal to 0. This is VDD minus RD times I over 2. All right. And let's now consider the case when VI1 is not 0. Let's make it 1 volt. But also make VI2 1 volt. If this is 1 volt and this is 1 volt, what happens? If you think about it, the perfect symmetry is still there. So it's still symmetrical, and therefore the analysis that we just did when this is 0 and this is 0 still applies. When this is 1 and this is 1, I still have perfect symmetry, and this current will still be I over 2. This current will still be I over 2, and the output voltage will still be VDD minus RD I over 2. All right, let's say now that VI1 and VI2 are sine waves, are signals. If this is a sine omega t here, so VI1 is a sine omega t, and VI2 is also the same sine omega t. Yeah, almost. Let's draw a better one. All right, so this is sine omega t and this is sine omega t. Even though they don't look exactly the same, they are exactly the same. So this is a signal here that's sine omega t volt. This is a signal here that's sine omega t volt. What is the output? What is the condition now in the circuit? Well, I still have perfect symmetry because this is sine omega t and this is sine omega t. So this is rising and falling. The voltage here is increasing to 1 and then decreasing to -1. But also, as this increases to 1, this also increases to 1. As this goes back to 0, this goes back to 0. As this drops to -1, this drops to -1. So there's no difference whatsoever at any time instant. The two voltages are equal. At all time, the two voltages are equal. This is always equal to this. Okay, so they're both sine functions, but they're always equal. So they're always equal, and therefore I always have perfect symmetry. This side of the circuit is exactly the same as this side of the circuit. So at all time, I will have a current here which is equal to the current here. And their sum is I, and therefore I will have I over 2 here and I over 2 here. So I over 2 and same here. Also I over 2. So the current that's flowing in the MOSFET, the current that's flowing here and the current that's flowing here are DC currents. Even though this is a sine wave, this is changing with time, the current here does not feel that, neither does the current here. They are DC currents. And what happens at the two drains, at VO1 and VO2? They're constant values. In other words, they don't feel what's happening here. So what does this mean? It means that the circuit is not reacting to the signal. The circuit doesn't feel it. It's actually rejecting it. And if you think about it, that's actually a good thing. Because if the two inputs are equal, this means that their difference is 0. And if the difference is 0 and I'm building a differential amplifier that amplifies difference, and the difference is 0, I don't want any output. This, even though it's DC and there is some value here, it's not 0 volt total, there is some DC, but there is no signal. There is 0 signal here. This is a sine wave, this is oscillating, rising and falling, and rising again, and so on. This is pure DC. This has no idea whatsoever that there is any variation at the input. It's a pure DC. So that's a good start. This circuit, we showed now that this circuit, given the two matched MOSFETs and the two equal resistors, would reject equal inputs. But that's not enough. We need to show that it likes unequal inputs. It amplifies differences. This is the BJT version. And again, we use bipolar. We can use bipolar instead of MOSFETs, so Q1 and Q2. And we use equal resistors, RC and RC. And we use two inputs at the bases. We connect the two emitters and use a bias current I and take the outputs from the collectors. The exact same analysis would apply with just a minor difference, I would say, that the current here would be I over 2 and the current here would be I over 2. But in the case of the BJT, when it's in the active region, and these two should be in the active region, the current in the collector will not be exactly equal to the current in the emitter. There is a small difference, which is alpha. So the current here would be alpha I over 2, and the current here will be alpha times I over 2. Because of the base current. The difference between alpha I over 2 and I over 2 is the base current. It's I over 2 over beta plus 1. But other than that, I get the exact same thing. So here I get when VI1 is equal to VI2, I get I over 2. And here I get alpha I over 2. And I get a DC level at the output as long as the two inputs are equal, and they can be sine waves, triangular waves, square waves, شو ما كان, whatever wave. If the two waves here, this wave and this wave are equal, if the two signals are equal, this will be a fixed DC level, will feel nothing whatsoever. And therefore, again, the BJT circuit very nicely rejects equal inputs or common inputs. But remember, Q1 and Q2 have to be matched, RC and RC have to be equal to be able to assume perfect symmetry. So again, now let's use the term common mode. This is our the MOSFET differential amplifier, and these are the two inputs. When they are equal, we call them common mode. So when this is equal to this, we use VCM. When VI1, common mode input, VI1 is equal to VI2 equal to VCM, we analyze the situation, and we got that the two drains would be at exactly this level, and there's no signal. This doesn't depend on VCM. Whatever VCM is, I get just a DC level here. Doesn't react. This is the result that we discussed. And now let's prove the other side of the equation, that we need to show that this amplifies differential signals. We said that it doesn't react to common mode signals. When the two inputs are equal, we call that common mode, and this circuit does not like them. Doesn't like common mode inputs, rejects them. The output will not react to common mode inputs. But now we need to show that it reacts to differential inputs. It amplifies differential signals. So here's what we will do. We will assume that the input is some DC level, which is the same here. So, and on this side, I have a plus VID over 2, and on this side, I have a minus VID over 2. So that the difference between VI1 and VI2 is VID. This is what we derived previously when we said that if I have two general inputs, VI1 and VI2, I can do a transformation into a common mode input and a differential input. So VCM plus VID over 2 and VCM minus VID over 2. We're assuming that the common mode input is DC, but it doesn't matter because we said whether it's DC or non-DC, the output will not react to it. So half of the differential input can be put here, and the other half, the minus VID over 2, can be put on the other side. And now what we want to show is that the output is some gain, which is hopefully large, times VID. Okay, let's do a small signal analysis to show that. So starting from here, I will use something that we haven't used a lot, the T model of the MOSFET. The T model of the MOSFET that looks something like this. Let me show it here. Actually, it's shown here. This is the T model of the MOSFET, GM VGS, and 1 over GM. Gate, drain, source, and GM VGS here. All small letters, and 1 over GM here. A resistor equal to 1 over GM. This is the T model of the MOSFET. If we have small RO, it will appear between drain and source. But for now, for simplicity, I will not include it. I will replace in my small signal analysis Q1 by its small signal model, Q2 by its small signal model, RD will remain there. This RD will remain there. This will become ground. This will become an open circuit because it's a DC current source. This becomes open. So I will have a T model here, a T model here, an open circuit here, and then RD to ground, RD to ground. And this is what we show here. The T model of Q1, the T model of Q2, RD to ground, RD to ground. And then here, nothing, right? Because there was a DC current source, it becomes an open circuit. And I have a VID over 2 and a minus VID over 2. Between the gate 1 and ground, I have VID over 2. Between gate 2 and ground, I have VID over 2. So between the two gates, I have a VID. All right. Question to all of you. What is the voltage here? What is the voltage at this node? Let's see, how many students do we have? We have at least 22. So the first answer is VID over 2. The second answer is average of VG1 and VG2. Any more guesses? Let's see. Let me ask at random some students. Sharbil, Bustani, any guess? Okay. Hiba, any guess? Thinking. Frangiye. No answer from Frangiye. All right. Yara is guessing it's VO2 minus VO1. Okay, I'll repeat the question. What is the signal here at this node? What is the signal here? I'm spending some time on this question because it's important in our coming analysis. We will refer to the answer. All right, two more guesses, VGS1 plus VGS2. VGS1 plus VGS2. Also VO1 minus VGS1. Let's try to analyze what do we have here. I have a voltage here, which is VID over 2, and then a resistor 1 over GM. and then this node, and then another resistor 1 over Gm, which is exactly equal to the previous resistor, and then a voltage here, which is minus VID over 2. So the circuit looks something like, someone is insisting on calling me. So let's say let's see. I will redraw this part of the circuit. I will redraw this part of the circuit, and this is what we have. Okay, this is the first gate, which is VID over 2. The second gate here is minus VID over 2. The first resistor, 1 over Gm. The second resistor, 1 over Gm. And the voltage here is what I want to know. What's the voltage here? Well, Muhammad Faqih guessed it. He guessed 0. And in fact, it is, because we can show that the current, we don't need to show, just use Ohm's law. The current here is VID over 2 minus VID over 2. So VID is the voltage drop in the 2 resistors. The current is VID divided by 1 over Gm plus 1 over Gm. 2 over Gm. All right, so this is the current flowing like this in the 2 resistors. So what's the voltage here? It's VID over 2 minus 1 over Gm times VID over 2 over Gm. And if you simplify, you'll get VID over 2 minus VID over 2. And as Faqih guessed, it is 0. This is an important result. I have a signal here, and I have a signal here, VID over 2, and I have minus VID over 2. And here I have no signal. Even though this is not connected to a DC source or connected to ground, hardwired to ground, or to any DC source, the conditions of the circuit make the signal here 0. And these conditions, we call them the seesaw conditions. Seesaw, you know what the seesaw is, right? The seesaw is like this. No, not like this. Like this. And then when this rises, this falls. And this rises as many centimeters as this falls. Here in this circuit, this is the first gate, and this is the second gate. And because this falls or rises as much as this does, but in the opposite direction, the node in the middle stays at no change, at no movement, no signal whatsoever. Even though this is not wired to anything, neither a DC voltage source nor a wire to ground, we see no signal here. Even though Hone, I will have maybe a signal like this, and Hone, I will have the negative of it. لأنه إذا في عندي VID over 2 here, I have minus VID over 2. So this is VID over 2, this is minus VID over 2. Hone, what do I see? What kind of sine wave? No sine wave. I don't see anything. This is at 0 signal. All right. So we answered this question, and it is 0. We call this a virtual ground because there's no signal. It's signal ground, but it's not a wire to signal ground. We call it virtual ground. I can place a virtual ground here and a virtual ground here. Let's extend the analysis using what we just learned, that I have a virtual ground. You see here the gray ground. It's a virtual ground. No signal. We see no signal here. And remember, we see no signal here when I have differential input. So V plus VID over 2 here minus VID over 2 here. And now let's find the output, and let's hope that the output is some amplified version of the input. So this is GM VGS, in this case GM1 VGS, but the two GMs of the two MOSFETs are the same because they're biased at the same DC conditions. So this is GM, I don't need to say 1 or 2, GM VGS, VGS1. VGS1 is VID over 2. Why? Because S1 is at signal ground. VG1 is VID over 2, and we showed that VS1 is a signal ground. This means that VGS1 is VID over 2. And let's see. This one is GM2, so again GM, VGS2, which is minus VID over 2. So I have a GM VID over 2 going up. All right, so we're getting close to calculating VO1 and VO2. Let's calculate VO2. The current flowing in RD is GM VID over 2. And when it flows in RD and I have a ground here, it produces the output. So finally, this is the signal at the second drain, VO2. The signal is GM VID over 2 times RD. Similarly, the signal here is minus, because the current is flowing like this, minus GM VID over 2 times RD. And this is an interesting result. I have a voltage here, which is minus GM VID over 2 times RD, and I have a voltage here, which is GM VID over 2 times RD. GM, of course, is ID over half VOV for the MOSFETs, and the two MOSFETs are biased at 1/2 the current source current, I over 2. So this is the GM value. So are we amplifying then? Of course. If I take the output from one drain, then let's say VO1, what is the gain in this case? This is the difference that I want to amplify, and I get a gain of minus 1/2 GM RD. So if GM times RD is 20, I get a gain which is minus 10. That's a very good result because it shows that if I have a difference between the two inputs, the output at the drain here is minus 10 times this difference. So 10 times bigger with an inversion. Also, the output here will be 10 times bigger without an inversion. The output here at VO2 divided by VID is plus GM over 2 times RD. So the output at the second drain would be plus 1/2 GM RD. So here I have 10 times the difference, but with an inversion. Here I have 10 times the difference without an inversion. So if you want the output to be inverted, you take it from this drain. If you want the output to be not inverted, you take it from this drain. This is positive gain. VO2 over VID is a positive number. Here, VO1 over VID is a negative number. And what's even better is if you take the output differentially. So you take VO2 minus VO1. And in this case, you get double the gain because this is going opposite to this. So when you take the difference, you get half GMRD minus 1/2 GMRD, and therefore you get double the gain, and it's equal to GMRD. In the case of this differential amplifier, I have 4 possibilities for outputs, and it's up to you to decide which one you want. You can take the output from the first drain, you can take to ground, you can take the output from the second drain to ground, you can take the output from the first drain to the second drain, so VO1 minus VO2. You can take the output from the second drain to the first drain, or VO2 minus VO1. And if you take the output differentially between the 2 drains, you get double the gain. And this number, GMRD, can be made quite large in the case of MOSFETs. And this means that the amplifier is indeed amplifying differences. When the two inputs are not equal, what this amplifier does is not amplify one of them and neglect the other, or it will amplify their difference. When they're equal, it will not amplify anything. We will not see any signal at the output. When they're not equal, it will amplify their difference. So that's a nice result, and we can extend it for the case when we have some non-ideal things. Non-ideal things here when we consider RO and RSS. So what is RO and RSS? RO, we know RO is the resistor, the channel length modulation resistance here that appears between drain and source. So I have a small RO like this and a small RO like this when the MOSFETs have channel length modulation. We neglected those, but now let's include them. What about RSS? RSS is, remember the current source that was here, and we said that it's an ideal one, and in the small signal analysis it becomes an perfect open circuit. Now we will say that, okay, this may not be ideal. In fact, it will be implemented most likely using MOSFETs. So it will have some output resistance, which is not infinite. And RSS would be that output resistance of this non-ideal current source. So if we have a real current source, a non-ideal current source, and has an output resistance RSS, let's include it. And here I will not have an open circuit. I will have an RSS to ground. What do RO and RSS do then? If I consider the output resistance of the current source RSS, it won't matter actually, because the node at which we showed that the signal is 0, the node in the middle, the seesaw pivot, this node in the middle will still have no signal even if the current source is not ideal and has an output resistance RSS. So our analysis here that showed that this is a virtual ground, this will continue to be virtual ground even if there is no there is no ideal DC source here, and therefore I have like an RSS. This will continue to be no signal. حتى لو في RSS. So this RSS will be between a virtual ground and a real ground, and therefore it will have no effect whatsoever. A non-ideal current source would not affect my analysis, and I will still get the same thing. What about small RO? Small RO, back to here, I will draw it. It will appear like this. So our friend small RO is actually connected from the output to the virtual ground. And this means that it's actually, in this case, connected in parallel with RD, because RD is connected from the output to ground and RO is connected from the output to ground. So I don't need to repeat the analysis. I'll just take these results and modify them to say the differential gain when I take differential output is GM, RD parallel RO. And when I take it single-ended from one drain to ground, it is plus or minus 1/2 GM, RD parallel RO. And therefore, this is the generalized result now. If even when I have small RO and if I have a non-ideal current source that's biasing the differential amplifier, I now have these nice results. And they show that the differential amplifier completely rejects equal inputs and only amplifies differences. Let me take a question or two. If there are any questions, please ask on the group chat. Okay, let's move on then. To introduce this new concept called the half circuit concept. The half circuit concept tries to make the analysis of differential amplifiers similar to the analysis of something that we are very familiar with, which is the common source amplifier. So the assumption here is that we know really well how to analyze a common source amplifier, and we want to use that knowledge to analyze differential amplifiers. مش كل مرة, I don't want to repeat such a circuit and analyze it if I have a differential amplifier. Maybe I can simplify it to something I am very familiar with. And in fact, I do. If you consider the circuit here, and just consider 1/2 of it, then take this half. When the inputs are like this. Oops. Again. When the inputs are applied differentially, we said that we get a virtual ground here. This is 1/2 of the circuit, and I have virtual ground here, and this is the other half, and I have a virtual ground here also. This circuit corresponds to a MOSFET and a resistor to the supply, and the signal is applied to the gate. So if we go back to our MOSFET circuit, this is the half circuit on the left, and this is the half circuit on the right. When the two are applied differentially, so plus VID over 2 here and minus VID over 2 here, and we get a virtual ground. So this is virtual ground. So focus on this circuit or sub-circuit, half circuit. What is it? I have a MOSFET with input at gate, output at drain, source is grounded. Okay, it's a virtual ground, but still ground, and a resistor to the supply. This is no other than our very, very good friend, the common source amplifier. So because I am very familiar with the common source amplifier, I will try to, whenever I have such a case of a differential amplifier with inputs applied differentially and a virtual ground appearing between them, I can consider the half circuit and it becomes a common source amplifier. And now all the things I know about the common source amplifier, I can use them here. For example, I know that the gain of common source amplifier V out over V in, well-known result, minus GMR prime N. V out is VO1, the VO1 at the drain of Q1. And the input, in this case, in this particular case of applying differentially, my VID, on the first gate, I would have VID over 2. On the second gate, I will have minus VID over 2. But on the first gate, I would have VID over 2. So this is V in. And this is the formula, V output over V input for a common source amplifier is minus GMR prime N. And if I rewrite it, I get VO over VID equal to minus half GM RO parallel RD. So using the formula of common source, I could have derived the formula that we just derived on the previous slides, that VO1, the output at the first drain, divided by the difference between the two gates, is minus half GM RO parallel RD. And from now on, we will try to use as much as possible this technique called half circuit concept to simplify a differential amplifier into a common source amplifier and then use the common source formulas. This makes things much, much easier than analyzing the whole circuit. Common mode gain and CMRR. Well, شو common mode gain? Now we just said that there is no gain when the inputs are equal. Why are we mentioning gain for common mode? Let's consider the situation at the start again. If I have two inputs that are equal, VICM and VICM, and a current source, and I'm showing here a resistor in parallel with the current source. It's not really a separate element that is in parallel with the current source. I'm just showing it to tell you that this is not ideal and it has an output resistance. And so the non-ideal current source has an output resistance of RSS. I will apply the half circuit concept again. Can I do that? Well, look at the circuit, and if you draw a line in the middle, you will see that this RSS is like having two resistors equal to two RSS in parallel, and then the circuit will be symmetrical, right? You have actually perfect symmetry. RD, RD, MOSFET, VICM, MOSFET, VICM, MOSFET, MOSFET are matched. Current source split in the middle, two RSS from this side and two RSS from this side. So I can also use the half circuit concept to analyze this circuit when the two inputs are equal. And this is what we get. This is one half of the circuit, and this is the other half of the circuit. This is the half, and this is the half. The two halves in this case are exactly the same. Hella, you need to answer me. What kind of amplifier is this? And it's not a tough question. It's easy to answer. But I'll wait for your answers on the chat window. What kind of amplifier is the half circuit? Yara was the first to answer correctly. This is, Kaman, our good friend, common source with source resistance. The input is at the gate. The output is at the drain. The source is not grounded. The source is connected to a resistor, but the resistor, after the resistor, I have the ground. So this is a common source amplifier with the source resistor. Kaman. So now I can use the formulas for common source amplifier with source resistor to find the gain in this case. So let's do that. VO1 over VCM will be this. This is the formula of common source amplifier with source resistor. GMRD over 1 plus GM times the resistance between the source and ground, which is 2 RSS. So VO1 will be this, VO2 will be this. And this is surprising, less surprising, because we said that if the two inputs are equal, I should not see any output. So what just happened? Why are we seeing an output now? This is a signal, and it's equal to the input signal times this. Well, the reason is the non-ideality of the current source. If the current source is not ideal, it has an output resistance RSS, then I will see an output VO1, and I will see an output VO2, which is the common mode input times this, and the same appears at the two drains. So if I take the output differentially, because the two are equal, even if the current source is non-ideal, I will not get anything. But if I take it single-endedly between the drain and ground, I will get actually a common mode gain. And the non-ideality of the current source, if I take the output from one drain only, will make this amplifier a non-ideal differential amplifier. It will have a non-zero ACM and a CMRR, which is not infinite. Okay, let's not cover this slide. We will cover it next time. I will stop.